Hello everyone. Good evening, my dear students. So today, specially we'll talk about sampling distribution. It's a chapter on statistics. So in the previous chapter, we have learned about what is statistics. I will discuss again what is statistics and what is population, sample, and some other concept additional with that. In this chapter, we introduce the concept of a statistics and its sampling distribution. Then the concept of estimation of population parameters will be introduced. These concepts have very important roles in almost all the remaining chapters. And we have seen that for large sample of size n, the distribution of the sample approximately gives the distribution of the population. And so it is reasonable to believe that sample characteristic will be approximately equal to the corresponding population characteristics for large n. So that is valid for if you take large values of n. But in such approximation of population characteristics, we come across one problem. We shall explain the problem by considering the particular situation where sample mean is taken as approximate value of the population mean if it exists. So let's explain one by one. First, I will define once again the statistics. Let E be a given random experiment and S be the corresponding even space. It is better to denote this S by omega because in probability we have introduced the symbol capital omega for the even space. Also, let X be a random variable defined on the omega. Let x1, x2, xn, small x1, x2, xn be a sample of size n drawn with replacement. So samples are denoted by the small letters and their random variables are denoted by capital. Be a sample of size n drawn with replacement from the population of the parent random variable capital X. If we consider all possible samples of size n, then x1, x2, xn become real variables. And in this case, a real valued function is called a statistics. Real valued function of x1, x2, xn. So statistics, if you want to say in one sentence, any function of the sample values is called a statistics. Any function of the real values or any function of the real variables x1, x2, xn is called any function of the sample values is called the statistics. Just for example, sample mean x bar, that is denoted by x bar, x1 plus x2 xn by n. Sample variance s square, capital S square. That is why I told you not to mention s. So it's better to mention even space by omega because we have mentioned omega in the probability as a even space. So you have to define omega, right? So sample variance is capital S square and that is 1 by n summation I equal to 1 to n xi minus x bar whole square, etc. This is your sample variance. I equal to 1 to n, right? x1, x2, xn are the sample of size n. Now I will explain the main concept of this chapter, that is sampling distribution of statistics. Let f of x1, x2, xn be a statistics, that is any sample value function, any function of the sample values, where x1, x2, xn be a sample of size n drawn with replacement from the population of the parent random variable x. Now we define n random variables. We are defining n random variables x1, x2, xn such that xi takes the ith value of any sample of size n from the population of x for I equal to 1 to n. Okay. Then we can say that x1, x2, xn, etc. are mutually independent random variables, each having the distribution of the parent random variable x, right? So that is very important point. We are defining, first we defining n random variables x1, x2, xn such that xi takes the ith value of any sample size n from the population of x for I equal to 1 to n. That is valid for I equal to 1 to n. Then we can say that x1, x2, xn are mutually independent random variables, each having the distribution of the parent random variable x. The random variable corresponding to the statistics f of x1, x2, xn is f of capital X1, capital X2, capital Xn. As we know, the random variables are actually denoted by capital X, and samples values are small x1, x2, xn. So the probability distribution of this statistics, the probability distribution of f of capital X1, X2, Xn is called the sampling distribution of the statistics f of x1, x2, xn. So sampling distribution is nothing but the probability distribution of the function of random values. Those random values which are random variables which are mutually independent random variables, and each having the distribution of the parent random variable x. So this probability distribution of f of capital X1, X2, Xn is called the sampling distribution of the statistics. Okay, this is the main idea and the main concept of the sampling distribution of a statistics. So suppose for example sampling distribution of the statistics x1, x2, xn by n, that is the sample mean, is determined by the probability distribution of capital X1 plus capital X2 etc capital Xn by n. Okay, so sampling distribution of a statistic, for example, the sampling distribution of the statistics x1, x2, xn by n is determined by the probability distribution of, just your sample values are replaced by capital x1, x2, xn, that is the random variables. So this is actually sample mean. Your statistic is sample mean. And this is denoted by x bar. Now, next we'll give you the concept of a parameter of a population. Let x be the population random variable. Formally, if alpha is a characteristic mean, variance, mode, median, etc. of the population. So alpha is any characteristic, then alpha is called the parameter of the population, right? Let fx, f is a function of small x, be the distribution function of the population random variable x. It is usually seen that the distribution function fx may have a known functional form, but it may contain some unknown parameters. And that we have observed in probabilities also. For example, if the population is known to be normal m sigma population, then m comma sigma are the unknown parameters. You know that x is a random variable that follows normal m comma sigma squared distribution. Then your unknown parameters are m and sigma. So that is the concept of the parameters. That means population may have some unknown functional, may have some known functional form, but it may contain some unknown parameters. So m and sigma are the unknown parameters in this case. So from the population, you have to learn, you have to study about the unknown parameters. Now, next we will define and explain estimation of parameter. After that, we'll give you idea of different estimation. Let alpha be a parameter connected to the population of the parent random variable x. So let alpha be a parameter connected to the population of the parent random variable x. Also let x1, x2, xn be a sample of size n drawn from the population of x. A suitably chosen statistics f of x1, x2, xn which doesn't contain the unknown population parameter is called an estimate of the parameter alpha. If the probability mass in the sampling distribution of the corresponding statistic is concentrated near alpha. So that is the main concept. A suitably chosen statistics f of x1, x2, xn which doesn't contain in the unknown population parameter is called an estimate of the parameter alpha if the probability mass in the sampling distribution of the corresponding statistic is concentrated near alpha. That is, it is highly probable that an observed value of f of x1, x2, xn will lie in a given small neighborhood of alpha. Okay? Highly probable that an observed value of f of capital X1, x2, xn, it's a function of random variables, will lie in a given small neighborhood of alpha where x1, x2, xn are mutually independent random variables, each having the same distribution as the parent random variable x. That we have explained earlier. So that is called the estimation of parameter. That you want to estimate the parameter alpha. And there is a high concentration of the probability mass in the sampling distribution of the corresponding statistic is concentrated near alpha. So this is the estimation of parameter. There will be some neighborhood of alpha. Highly probable observed values are in this interval, lie in this interval, neighborhood actually. Next, I will define different types of estimates. So already I have explained estimation of parameter. Now I will explain different types of estimates. First, I will explain unbiased estimate. So let x1, x2, xn be a sample of size n drawn with replacement from the population of the parent random variable x. An estimate f of x1, x2, xn of a parameter alpha concentrated to the given population is called an connected to the given population is called an unbiased estimate if expectation of f of x1, x2, xn, that is the function of x1, x2, xn, will be alpha. Once again I repeat, an estimate of the statistic, this is a statistics function, any function of the sample values is a statistics. So an estimate f of x1, x2, xn of a parameter alpha connected to the given population is called an unbiased estimate if expectation of f of x1, x2, xn equal to alpha, where f of x1, x2, xn is the random variable corresponding to the function statistics, corresponding to the statistic, where x1, x2, xn are mutually independent random variables, each having the distribution of the parent random variable x. So in every line we are mentioning that thing, that the thing is that x1, x2, xn are mutually independent random variables, each having the distribution of the parent random variable x. In this case, the random variable f of x1, x2, xn is called an unbiased estimator of alpha. In this case, this f of x1, x2, xn, that is the random variable corresponding to the statistics, is called an unbiased estimator of alpha. So this is about the definition. You can say this is your definition and this is the explanation of unbiased estimate. Expectation of f of x1, x2, xn will be alpha. That is the unbiased estimate. And next one is consistent estimate. So it is the next type of estimates, consistent estimate. Again, let x1, x2, xn be a sample of size n drawn with replacement from the population of the parent random variable x, and estimate f of x1, x2, xn of a parameter alpha. Always the parameter is alpha. In this case, your parameter is alpha. So you are estimating the parameter alpha with the help of the statistics connected to the given population is called a consistent estimate if f of x1 x2 xn, that is the random variable corresponding to the statistics, tends to alpha in p as n tends to infinity. And already we have explained this tends to alpha in p in probability convergence chapter. You just learned the chapter of convergence that follows from the convergence is probability. That is for every epsilon greater than 0, its limit n tends to infinity, probability of mod f of x1 x2 xn minus alpha less than epsilon equal to 1. So that is the convergence of probability concept, where f of x1 x2 xn is the random variable corresponding to the statistics, and x1 x2 xn are mutually independent random variables, each having the distribution of the parent random variable x. In this case, the random variable f of x1 x2 xn is called a consistent estimator of alpha. So if you define the consistent estimate, if you want to define, this is your definition. This is your definition. But in this definition, the main concept is the convergence probability. So before that, you have to take care of your concept of convergence probability. And that concept lies behind the consistent estimate. Okay. So f of x1 x2 xn tends to alpha in p as n tends to infinity, as n goes to infinity. So actually in this interval, if you take the interval alpha minus epsilon and alpha plus epsilon, epsilon is a very small positive number, the maximum concentration of probability mass lies in this interval. Highly concentrated probability mass in this interval. So that is why this limiting concept is there. Okay. So there is a note for all of you. An estimate f of x1 x2 xn, that is the statistic, an estimate of the statistics of a population parameter alpha, will be called a good estimate of alpha if the estimate is both unbiased and consistent. So it will be a good estimator, or it will be a good estimate of alpha if the estimate is both unbiased and consistent. Next, I will prove some theorem, and some of the theorem will be given to you. You can try to prove those theorems, but those are very important theorems. First theorem, sample mean is a consistent and unbiased estimate of the corresponding population mean if the population mean m exists. So sample mean is x bar is a consistent and unbiased estimate of the corresponding population mean. That means if it is an unbiased estimate, that means expectation of x bar equal to m. And if it is a consistent, then x bar tends to m in p as n tends to infinity. That will have to prove, right? So let's start. Look at that. So once again, you have to start by collecting the sample of size n. So let x1, x2, xn be a sample of size n drawn with replacement from the population of the parent random variable x. Then the sample mean is given by x bar equal to x1 plus x2 etc. xn by n. Let m be the population mean. If x bar be the random variable corresponding to small x bar, then capital X bar is x1 plus x2 etc. xn by n, where x1, x2, xn are mutually independent random variables, each having the distribution of the parent random variable x. So this is your sample mean. This is your x bar with the random variable corresponding to small x bar, right? So this is your representation. Now since x1, x2, xn are mutually independent random variables, each having the distribution of the parent random variable x, then expectation of x1 equal to expectation of x2, etc. Expectation of xn equal to expectation of x equal to m. Now expectation of x bar equal to expectation of this whole thing x1, x2, xn by n, and 1 over n times expectation. If you split expectation, because it's using the properties of expectation, we can write this line, and these are all m. So there are, what is the number of m's? N m's. So it will be nm. Nn got cancelled, m is the result. So we prove that expectation of x bar is m. So we have proved that expectation of x bar is m. Hence, x bar is an unbiased estimator, and so small x bar is an unbiased estimate of the corresponding population mean m. Right? You look at the definition once again. If you want to see the definition once again, yeah, expectation of this equal to alpha. So this is called the unbiased estimator of alpha, right? So this is very simple proof, and this is very important. This is important proof, right? So you can go through the proof once again. Next, I will prove the consistent one. By the law of large numbers for equal components. Already we have explained in the last class, law of large numbers. I gave you the proof also. By the law of large numbers for equal components, we have x1, x2, xn by n tends to m in p as n tends to infinity. So x bar tends to m in p as n tends to infinity. Hence, the sample mean is a consistent estimate of the population mean m. This completes the proof. So we have seen that population mean, sample mean is a consistent and unbiased estimate of the corresponding population mean, if the population mean exists. That we have proved. Next, I will prove another theorem. This theorem is similar to this one, the previous one, so I will not prove this one. The sample kth moment ak is denote the a suffix k is the sample kth moment, is a consistent and unbiased estimate of the population kth moment alpha k, provided alpha k exists. So ak is a consistent estimate of the population kth moment alpha k, and unbiased estimate of the population kth moment alpha k. So you have to prove similarly, right? So this is for your assignment. You can do it by yourself. Next theorem, important theorem, is that sample variance h square, capital S square, is a consistent but biased estimate of the population variance sigma square. It is not unbiased. It is a biased estimate of the population variance sigma square. It is consistent and biased estimate of the population variance sigma. We'll prove that. This is very, very important, extremely important. So again, we have to take x1, x2, xn be a sample of size n drawn with replacement from the population of the parent random variable x. Then the sample variance is given by, this is the expression for the sample variance. You know that s squared is 1 over n times summation I equal to 1 to n xi minus x bar whole square, where x bar is the sample mean, right? Sample mean is given by x bar equal to x1, x2, xn by n. The random variable corresponding to s square is given by 1 by n. X will be replaced by capital X, xi minus x bar square, right? That is capital S square equal to 1 by n summation I equal to 1 to n. Okay, and this is your random variable corresponding to s square. So this, you can denote this by small s also. Okay, denote it by like this. You can use a symbol like this. This is a typographical. You can use a symbol small h square like this. Small h square for sample variance and capital H square for. So instead of using this, you can use this symbol. This is equal to small h square, right? This will be fine for statistic sample variance, and for random variable you can use capital H square, right? So if x bar be the corresponding random variable to the x bar, then capital X bar is x1, x2, xn by n, where once again I have to repeat the same statement. X1, x2, xn are mutually independent random variables, each having the distribution of the parent random variable x. Now look at that, your x is square. If you expand this expression, it is a whole square. So you can write xi square to x bar summation I equal to 1 to n xi 1 by n summation I equal to x bar square. So this is actually x bar square is constant. So if you add them n times, it will be nx square. And this summation I equal to 1 to n xy by n is x bar. So that will be 2x bar square. So ultimately you have this type of expression. A square is given by this, right? This is by calculation. It's a simple calculation. Now, here x1, x2, xn are mutually independent random variables. So their squares will also mutually independent. So x1 square, x2 square, xn squares are also mutually independent. And since x1, x2, xn have the same distribution as x, each xi square I equal to 1 to n has the same distribution as x square, right? Let expectation of x square is alpha 2. It's a moment, second order moment about origin. Then expectation of x1 square, expectation of x2 square, etc. equal to alpha 2. Because x1 square, all x2 square, etc. are all mutually independent, and they are having the same distribution as x square. So that is why we can write this one is equal to, all of them are equal to alpha 2. Therefore, by the law of large numbers for equal components, again we are using the large numbers for equal components, x1 square plus x2 square, etc. xn square by n tends to alpha 2 in P as n tends to infinity. That is by the law of large numbers. Also by the same law, x1 plus x2, etc. xn by n tends to m in P as n tends to infinity, where x1, x2, xn having the same distribution as x, so all these expectation is equal to m by the same law. So for the same law, we are using this tends to alpha 2 as n tends to infinity, and x bar, capital X bar tends to m as n tends to infinity. That is, x bar tends to m as n tends to infinity because this is your x bar, capital X bar, the random variable corresponding to the sample mean. And consequently, x bar square tends to m square in P as n tends to infinity. Right? Hence, x1 square, x2 square, xn square, this is by limiting. You know that in convergence in probability, if u tends to alpha and v tends to beta as n tends to infinity, then u minus v also tends to alpha minus v, alpha minus beta, and their plus also tends to alpha plus beta. That is the properties of the convergence, and there is a proof of that in the convergence chapter. So I'm using that theoretical part only in this case in statistics. So x1 square, x2 square, xn square by n tends to alpha 2. You see that this is the thing. So from 1, if you say this is 1 and this is by 2, this equation is 2. From 1 and 2 we can write this one. This is 3. So this is nothing but your alpha 2 minus m square is sigma square. Variance square. It's a variance. It's a variance. Standard deviation square. It's a calculation for variance. It's a formula. And this is your h square. Random variable corresponding to the sample variance. You see, this is your h square. This is your S square. S square is a random variable corresponding to the statistics small s square. So this is the thing. So I'm writing this S square tends to sigma square as n tends to infinity. Okay. So S square is a consistent estimator of sigma square. A square is a consistent estimate of sigma square. That is the proof. That is a very, very important proof for all of you. So that we proved here. Now we have to prove that it is not biased. It is not unbiased. That is, we have to prove biased. So let's check. Once again, we have to start from the random variable corresponding to the statistic small square. So S square is 1 by n. Again, this expression, if you write minus m plus m, we can write that. And this is suppose a, this is b. So you have to write a plus b whole square. So it will be in this form. A square plus b square minus 2ab. So again, you split and take the summation individually. So if you take the summation, you will get this type of this calculation. You can go through the calculation. So you can write ultimately after simplifying, you can get xi minus m whole square minus x bar minus m whole square. This is the expression. Now you can write expectation of h square. This is h square. This is x square. Now if you take expectation both sides, expectation of h square is 1 by n summation I equal to n expectation of xi minus m whole square and expectation of x bar minus m whole square. And since x1, x2, xn all having the same distribution of x, x1 square, x2 square, xn square all having the same distribution of x square of the parent random variable, so we can write this term that all is sigma square because all follows the parent random variable, that is follows the population. So expectation of x bar is given by this also once again, and this is equal to m. Already we have proved in earlier steps. So expectation of x minus m square is nothing but your variance of x bar, and that is variance of x1, x2, xn by n. And from the variance property, 1 by n square variance of x1 plus variance of x2, etc. variance of xn. If you split this term, so this is equal to 1 by n square, and variance of x1 is, you look at that, your variance of x1 is expectation of x1 minus m square. Yeah. And expectation of x2 minus m square, this should be x2, this should be xn, right? And all having the same variance sigma square. These all having the same variance sigma square. So it is n sigma square. So ultimately it is sigma square by n. So now what is your expectation of h square? Look at that. Yeah, this is your expectation of h square. Okay, this is. So this part is, you have this part and this part. This part is, the first part is n sigma square by n, and the next part is sigma square by n. Ultimately you are getting n minus 1 by n into sigma square, right? N minus 1 by n sigma square, that is not equal to sigma square. So this is not unbiased estimate. It is a biased estimate of the corresponding population variance sigma square. So this is the long calculations, but it is not so complicated. Just you need to calculate this part. This is n sigma square, right? This is n sigma square, this part. And this is calculated here. This is your sigma square by n. So I'm writing these two part, and finally you have n minus 1 by n sigma square. Very, very important relation, and that is not equal to sigma square. Because for unbiased estimate, you have to get expectation of h square equal to sigma square. Otherwise, it can't be a unbiased estimate. So that is why it is a biased estimate of the population sigma variance sigma square. Okay. Now next theorem. So you have an idea about these two important theorem I've discussed about the idea. So you can generalize the concept and prove other theorems in this chapter also. So I will explain more. You can try this theorem to prove. Without any proof, I will explain more theorems. So if the population for which samples are taken is normally distributed with mean and variance sigma square, then the sample mean is normally distributed with mean and variance sigma square by n. Okay, so this is very important. If the population, if you are talking about a population for which samples are taken is normally distributed with mean m and variance sigma square, then the sample mean, so your sample mean is x bar, is normally distributed with mean m and variance sigma square by n. So your population, your normal sample mean follows normal distribution with mean m and variance sigma square by n. This sigma standard deviation of this sample mean is sigma by root n. This is sometimes called standard error. Sometimes I will explain later on, not in this lecture, next lecture. So that is very important. Now there is a theorem. You can try this, please, all of you. Try this theorem. This theorem can be proved by characteristic properties also, because you can use this theorem to use characteristic function. I'm just giving you a hint because characteristics function determines the distribution uniquely. Yes, there is a theorem. Characteristic function determines the unique distribution functions uniquely. So that is why you can use characteristic functions for proving this theorem. So proof is required for this theorem. Next, show that for a normal m sigma population, x bar minus x by sigma by root n is a normal 0, 1 variate. You see your your x bar is normal m comma sigma. If you write the variance sigma square by n variate, so naturally your, if you take the transformation, it will be x bar minus x by sigma by root n is a normal 0, 1 variate. So if you take this is as y, I'm just giving you a hint how to prove. This is equal to y, then in real variable it will be x bar minus m by sigma by root n, right? This is your real variable. So if you write dy dx, that is the transformation, you can use the transformation root over n by sigma, right? So I'm differentiating with respect to x bar. Yes, this is your x bar. This is your x bar. So the root over n by sigma is positive for all x bar. For all x bar, this is positive, right? So the transformation you can use fyy equal to f x bar mod dx bar dy, right? So okay, this is the thing. So I'm writing fx bar x, that is your 1 by root over 2 pi. I'm using the standard normal distribution formula. So in this case your normal m comma sigma by root n, right? So it is sigma by root n, right, e to the power, if you are right, minus half, okay, x bar minus m by sigma by root n whole squared into sigma by root n. Just I am using this transformation rule for distribution. Okay, so finally you will get 1 by root over 2 pi e to the power minus y square by 2. minus infinity less than y less than infinity, right? Hence y is normal 0 comma 1, right? That is the proof. That is a very simple proof and important also. So you can use this thing. This is the proof. Okay. Next, for a normal m sigma population, the statistics n square by sigma square is has a chi-square distribution, with n minus 1 degrees of freedom. N minus, oh, okay, this statistics you can write small s square also, and where n is the size of the sample drawn from the given population, where s square is the random variable corresponding to the sample variance. Sample variance is small s square, right? What I'm talking about. Okay, so this gives you the another important theorem. If for a normal m sigma population, thus this is the statistics. This statistics actually follows as a chi-square distribution. We have explained the chi-square distribution. And for a normal m sigma population, the statistics root over n into x bar minus m by s over s has a t distribution. We have explained in the previous class t distribution, chi-square distribution, and f distribution with n minus 1 degrees of freedom, where n is the size of the sample and small s square is given by n minus 1 s square, right? A square being the sample variance. Okay, this is your sample variance. N square, a square, capital A square is the sample variance. So this is the important theorem. So these are all important things you have to learn about your sampling distribution, and more things. If the population is with replacement or without replacement, I will discuss in the next class, and I will do some problems on to give you more idea about the sampling distribution. I will give you more problems solving and some theoretical concepts in the next class. So follow my lectures and follow my videos on YouTube. Thank you all.